Thank you, and thank you for the introduction. The Large Hadron Collider in Geneva at CERN is currently the world's largest particle collider. It collides protons in a tunnel that is 100 meters under the ground, about 27 kilometers long. And the protons are collided in a controlled way at 4 different locations around the circle, where particle physicists then collect the data that is produced in these collisions with the purpose of finding out what matter is made of. The Large Hadron Collider has found one fundamentally new particle that is called Higgs Boson, the discovery of which was announced in 2012. I'm sure that a lot of you recall the headlines, recall the photos of physicists that were celebrating, popping the champagne. A lot of you will probably also recall that before the Large Hadron Collider started operation, that was in 2010, a lot of physicists expressed themselves very confident that it would see something else besides the Higgs boson. There was a lot of talk about other new particles, most prominently probably the supersymmetric particles. They also hoped that it would see evidence for dark matter, would find new particles that could explain that. There was also a lot of talk about the possibility of seeing additional dimensions of space, maybe produce tiny black holes. This is something that I wrote my PhD on. Some people were talking about making contact to parallel universes. There was certainly a lot of hope in the atmosphere, and none of that became reality. What happened here? Why were all those predictions so terribly wrong? Now, since it's in the title of my talk, I think I'm not giving away too much if I say that I think that physicists have been led astray by the beauty of their theories. And in the rest of my talk, I hope that I will manage to explain just what has gone wrong here. Before I do anything else, I have to tell you, though, just exactly which fields of physics I'm talking about. There are many fields in physics. There's nuclear physics, there is optics, quantum informations, astrophysics, and so on and so forth. And I'm talking about a particular part of that large community, which I summarize as the foundations of physics. That are those areas where we deal with the natural laws that cannot be derived from any other underlying laws. And in these areas, we currently have 2 types of theories. That is, on the one hand, the theory of general relativity that goes back to Einstein, which describes the behavior of space and time. And then we have what is called the standard model of particle physics that describes the smallest constituents of matter and the interactions between them. So this is what I'll be talking about in the rest of the talk. What has been going on in these areas as of recently? We have heard a lot of talk about a crisis. There's a crisis in physics, a crisis at the edge of physics, at the foundations of physics. It has something to do with supersymmetry. Could there be a crisis in physics? Another crisis in physics. Is theoretical physics in crisis? You could get the impression. And this is my favorite. This is an article which recently appeared in New Scientist. We will die before we find the answer. That's quoting Neil Turok, who is the director of one of the most influential research institutions in the foundation of physics, the Perimeter Institute. Yes, what's going on? Why all this talk about crisis? There has not been a lot of progress in the foundations of physics in the past 40 years. Those theories that I've been talking about, general relativity and the standard model, are fairly old. General relativity is indeed more than 100 years old. And the development of the standard model was largely completed in the mid-1970s. Yes, after this, we have added some more parts to those theories. For example, general relativity, we have added back the cosmological constant that Einstein already had, and then it was widely believed to be zero. Then it turned out 20 years ago, it's not zero after all. So it's back in again. But this has not really changed the theory. In the standard model, we have added some more particles that were only discovered later, the latest being the Higgs boson that I was already talking about. We have also added masses to the neutrinos, but the theory for the neutrinos dates back to the 1950s. Also, the theory for the Higgs boson dates back to the 1960s. None of what has happened past the development of the standard model in the 1970s has really changed anything about the mathematical formulation of the theories that we're using. They're basically still the same theories. But it's not we're done. Like we can just pack and go home and say physics is over, that's it. We do have some unsolved problems in the foundations of physics that we know require a solution. For example, the standard model does not fit together with general relativity. As you've probably noticed on the first slide that I showed, I had general relativity separate from the standard model of particle physics. That's because the two don't like to work together. The problem is embarrassingly easy to understand and terribly hard to solve. What's going on here is that we know that the particles that are in the standard model have quantum properties. Or they're good old friends like the electrons and the neutrinos and so on. That they have quantum properties means, among other things, that they obey Heisenberg's uncertainty principle and they can be in two places at once. Now, we know that most of those particles have masses, and masses generate a gravitational pull. This brings up the question, if you have a particle that is in two places at once, where does the gravitational pull go? This is a question that Einstein's theory of general relativity cannot answer because it doesn't know anything about quantum properties. And to answer this question, we need what is known as a theory of quantum gravity, that since Einstein's theory actually describes the curvature of space and time, would be a theory about the quantum properties of space and time itself. So this is a problem which has been known since the 1930s, that we need a theory that can accommodate quantum effects in gravity, but we still don't know what this theory is. We have other problems. For example, there is so-called dark matter that astrophysicists think constitutes 85% of the matter in the universe. We don't know what it is. We know that it cannot be made of any of the particles that we have in the standard model. That would not work. Indeed, we're not perfectly sure that it is some kind of a particle to begin with. There is an alternative explanation for the observations, which is that it's not the matter sector that we're misunderstanding, but that it's actually the gravitational part that we're misunderstanding. And we have to change something about Einstein's theory of general relativity to explain the observations that we have in the cosmos. Either way, we have to change something about the foundations of physics to explain these astrophysical observations. And then we have other problems that you probably hear other colloquia about. For example, how did the universe begin? What happens in the inside of black holes, and so on and so forth. No, it's not that we're done. We do have problems that we need a solution to, and we have not made progress on that in the past 40 years. It is certainly true that these are hard questions, and it is fair to expect a slowdown in progress as a discipline becomes more mature. Physics is one of the oldest scientific disciplines, and the simple things have been done. So on that level, that progress slows down is not so surprising. For this reason, I also don't really like all this talk about crisis. A better question is progress as fast as it could be. Are we doing the best that we can to make headway on those problems? And I think the answer to this is no, almost certainly not, because physicists focus on the wrong problems. So just what happened here. I'm not a historian, but I will now try to give you a brief summary of what has historically happened in the foundation of physics in the past couple of hundred years. I have, since the publication of my book, gotten a lot of feedback from people in the philosophy and history of science, and they have told me that I got it it's not totally wrong what I'm about to tell you. I'll start with Isaac Newton about 400 years ago, for whom beauty used to be a sign of godly influence. And Newton wrote, "This most beautiful system of the sun, planets, and comets could only proceed from the counsel and dominion of an intelligent being." Newton was by no means an exception at his time. It was fairly common back then to think of the laws of nature as being written by God. Of course, God is good, and so God would have chosen laws that are beautiful. It was just natural to identify those two things with each other. Then as science progressed, these references to God fell out of favor, and people tried to avoid them. So here we have Henri Poincaré around the turn of the century, from the 90s to the 20th century, for whom beauty basically was a bonus of his profession. He wrote, "The scientist does not study nature because it is useful to do so. He studies it because he takes pleasure in it, and he takes pleasure in it because it is beautiful." He was grateful that he found this beauty in the laws of nature. As physics progressed, beauty turned into a guide. Here we have Hermann Weyl. Hermann Weyl was actually not a physicist, he was a mathematician, but he did make some very important contributions to the development of the theory of general relativity and also gauge theory. He wrote, "My work always tries to unite the true with the beautiful, but when I had to choose one or the other, I usually choose the beautiful." Then we have Paul Dirac, who went one step further and actually declared beauty to be a mandate of the research worker. The research worker, in his efforts to express the fundamental laws of nature in mathematical form, should strive mainly for mathematical beauty. And this is by no means the only time that he said this. He made several similar statements throughout his career. And as physicists became more successful, they became increasingly convinced that they can understand nature by pure introspection, by looking inside them and just trying to feel what nature wants. So here we have Albert Einstein, who wrote, "I am convinced that we can discover by means of purely mathematical constructions the concepts and the laws connecting them with each other, which furnish the key to the understanding of natural phenomena. In a certain sense, therefore, I hold it true that pure thought can grasp reality as the ancients dreamed." To be fair to Einstein, in other places he did emphasize the need to make contact to experiment. With Einstein, I want to leave behind the realm of the ones who are already deceased and come to those who are still alive, starting with Anthony Z, who is a professor at the University of California in Santa Barbara. And in the 1980s, he wrote a book about symmetry in physics, where he wrote the following: "My colleagues and I, we are the intellectual descendants of Albert Einstein. We like to think that we too search for beauty." So you see here how this idea that beauty is a guide to the discovery of new laws of nature was handed over from one generation to the next. Here we have Steven Weinberg. Steven Weinberg won a Nobel Prize for the development of the Standard Model. He wrote a book in the 1990s, which is called Dreams of a Final Theory, in which he makes an analogy to a horse breeder. He writes there, "The horse breeder looks at a horse and says, 'That's a beautiful horse.' While he or she may be expressing a purely aesthetic emotion, I think there's more to it than that. The horse breeder has seen lots of horses, and from experience with horses knows that's a kind of horse that wins races. What he's basically saying here is that we have collected a lot of experience with theories that work in physics. And now if we try to decide if a theory is going to be successful, if it's going to win a race, then we can rely on that experience that we have collected from the past. And this is all well and fine, except that it only works as long you are staying within the same class of mathematical structures that you use for your theories. If you're dealing with a theory that is really dramatically different, then the sense of beauty that you have extracted from the successful theories of the past may no longer continue to be useful. Here we have another Nobel Prize winner, Murray Gell-Mann, who won a Nobel Prize for the development of the quark model. He said this in a TED talk that you can find online. What is especially striking and remarkable is that in fundamental physics, a beautiful or elegant theory is more likely to be right than a theory that is inelegant. I strongly doubt that this is correct, but this is what he said. And then I have one final quote here from Robert Dijkgraaf. Robert Dijkgraaf is a string theorist and currently the director of the Princeton Institute for Advanced Study. He has written, once you have understood the language of which the universe is written, it is extremely elegant, beautiful, powerful, and natural. The universe wants to be understood. And that's why we are all driven by this urge to find an all-encompassing theory. I guess some of us more than others. Before I say anything else, I have to tell you exactly what those physicists mean when they talk about beauty. For my book, I traveled around and I spoke with a lot of physicists about what beauty means to them, what they mean when they say that a theory is beautiful. And maybe the most surprising thing that I found was that they all largely agreed what they mean by beauty. In the following, I will try to summarize this notion of beauty that physicists are using. And I want to put ahead that by no means do I want to tell you what beauty should mean to you. I'm just summarizing what those physicists have told me. And I have here a photo of a little flower arrangement that my children made in the garden. It's not exactly a masterwork of art, but I think it does capture some elements of beauty that we all recognize immediately. The most obvious one of which is that it has a lot of symmetries. It has a very simple kind of symmetry. It is also natural in an obvious way by using natural ingredients, but also because it's not too rigid. It has a certain randomness sprinkled over it, and it is, in a very straightforward way, simple. And I think that these elements of beauty are also what we find in the foundations of physics. Let me start with simplicity. There is a notion of simplicity that is a good scientific criterion, which is relative simplicity, that you may be familiar with as Occam's razor. Relative simplicity basically says if you have several theories that achieve the same, then you pick the one that is simplest. Because why would you want to make your life more complicated than it has to be? So this is good scientific procedure, and this is not what I'm talking about. What I'm instead talking about is absolute simplicity. You want a theory that is simple, period. That means concretely that it should have a small number of assumptions. And in practice, this is presently typically achieved by symmetry requirements or the attempt to unify different phenomena into one. A good example is here the standard model of particle physics, which contains three different forces. There's the electromagnetic force, and then there's the strong and the weak nuclear force. A lot of physicists would rather have only one force, one unified, grand unified force, that's what it's called, from which those three different forces would come out at low energies that we have tested so far. This trend towards simplification and unification is to some extent experience-based. It is something that has worked in the past in several instances, but we do not know whether it will continue to work. It is certainly something that you may try, but it is, after all, only hypothetical if you try to apply it for the next deeper law. To illustrate the relation to art, I have brought you this wonderful photo from a photography style that is called minimalism. The problem with making arguments from simplicity is that the world is only so simple. There are a lot of theories that we can think of that are simple in absolute terms, but just do not describe the world that we see around us. For example, if you had a universe that does not contain any matter, that would be much simpler than having to bother with all this stuff here, but it would also be wrong. Or to use a somewhat less nihilistic example, if you try to quantize gravity in 2 dimensions, it's much simpler than doing it in 4 dimensions. It's just that we don't live in 2 dimensions. There's that. I think that Einstein actually said it very well when he wrote, you should try to make it as simple as possible, but not any simpler. My understanding of which is that eventually you always have to ask, what is it that actually describes the observations that we have? The second ingredient of beauty for theoretical physicists is something that goes under the name naturalness. People who do not have a background in physics tend to find this the most difficult aspect of beauty. It basically means that the pure numbers that we have in our theories, so those without units, should be approximately 1, not exactly 1, but also not much larger than 1 and not much smaller than 1. The reason why this is called natural, I have brought you this little picture here that I took of a sunflower field. If you look at this field, you see a lot of sunflowers that they kind of look similar. They have about the same height. They have about the same size. It's not exactly the same height, not exactly the same size, but they're kind of pretty close by. If you were to take ratios between those sizes and you would do this to get a number that doesn't have units, then you would get numbers that are close by 1. They would not be exactly 1, but kind of in this ballpark. If you were to walk by a field of sunflowers and you would see a sunflower that is 1 million kilometers high or something, you would say, that's unnatural. That requires an explanation. And that's the same attitude that particle physicists bring to unnatural numbers in their theories. They think it requires an explanation if you have a number that is very small or very large. In high-energy particle physics in particular, we have another notion of naturalness, which is called technical naturalness. Technical naturalness is actually a slightly weaker criterion than this general naturalness, which says that some small numbers are allowed if you have an explanation for why they are small. An explanation can, for example, be a symmetry. If you recall, I mentioned in the beginning there was this idea that the Large Hadron Collider should see supersymmetric particles. The main reason for why a lot of physicists thought this should happen was technical naturalness. So if you look at the standard model of particle physics and you look at all the dimensionless numbers that appear there, then they are all natural. They are all technically natural, except for one number, which is the mass of the Higgs boson. And since that does have units, you still have to divide it by something that's called the Planck mass. It doesn't really matter what the Planck mass is. The point is that this gives you a very small number, which is 10 to the minus 15. And this number does not have an explanation. Particle physicists consider this to be very ugly. What they do is that they amend the standard models that this small number has an explanation. And supersymmetry provides an explanation for why this number is small, provided that the additional supersymmetric particles would appear at the Large Hadron Collider. Well, this is how this argument goes. The standard model is not pretty enough. We're trying to make it prettier, and as a consequence of this, we would have to see these additional particles at the Large Hadron Collider, which has not happened. Ultimately, the reason why physicists believe in these arguments from naturalness is that they try to avoid something that they think is improbable. The reason that they do not want to have a very small parameter is that it seems improbable that you would get such a small number if you were to choose it randomly. The problem with that kind of argument is that you are talking about a fundamental parameter of nature. We have no idea whatsoever what the probability is for finding that parameter, and we also have no way to ever find out what this probability was, because there's no way that we can sample different universes with different values of that number. We do not have a probability distribution, and we can also never get it. Without this probability distribution, naturalness is merely an aesthetic criterion and not a scientific one. Then there's the third aspect of beauty, which is also the most elusive one, which is often referred to as elegance. It basically means that you get a lot out of a little. You want a theory that is simple, yes, but you don't want it to be too simple because that would be boring. Sometimes people have put it to me as making new connections or as getting surprising insights. Some philosophers have called it unexpected explanatory closure. Basically, what they're all talking about is that you want an aha moment, a theory that explains something that you did not understand before. To illustrate this aspect of beauty, I have brought you this amazing image from an art style that is called fluid art. You can see some videos of how this is made on YouTube. The way that it works is that you have a glass in which you mix different colors of acrylic colors, and you add some chemicals to it, and then you turn over the glass and put it on a canvas, pull away the glass, and it will run apart and form these amazing structures. It's a very simple idea out of which you get a lot of surprises. Examples of elegant theories in the foundations of physics are, for example, general relativity. General relativity is really a very simple idea. Now, Einstein would maybe be surprised to hear that because he struggled very hard to develop this theory. But that was because he did not have the mathematical apparatus at hand. He had to develop the mathematics along with the theory. But if you already know the mathematics, if you know differential geometry and some topology, then it is pretty simple to derive Einstein's field equations. It is a pretty simple theory, but it also brings a lot of unexpected insights. For example, it gives rise to black holes. It gives rise to gravitational lensing. It gives rise to gravitational waves. Maybe there are wormholes. There's the redshift in the gravitational fields. So these are all consequences that you don't just see from looking at these equations. For this reason, I think general relativity is widely said to be a very elegant theory. Another example of a very elegant theory is string theory. String theory starts from a very simple idea. Everything is made of strings. But once you try to formulate this in a mathematically rigorous way, then this so simple idea develops its own will. It will, for example, tell you that to make this theory properly work, you need to have more dimensions of space. You need 10 in total. It will also tell you that you need supersymmetry, and it has some other surprising consequences. So again, this simple idea that leads you to new insights is considered to be very elegant. The problem with elegance is that it strongly depends on your knowledge and on your education. Whether or not you find something surprising depends on whether or not you expected it. And the more you know of a theory already, the more likely it is that you expected it to happen. So really, it's a very subjective criterion that also changes with time. The more you work on a specific theory, the higher your tolerance for more complicated explanations may be. So taken together, these three aspects of beauty is what I call the hidden rules of physics. In practice, they have become converted into technical requirements, and their status as hypothesis has become forgotten. People are just using them when they are trying to develop a new theory, which they then may set out to test. This is particularly obvious when it comes to naturalness. And naturalness is quantifiable for certain theories. They are just equations that you can use to calculate how natural a theory is. And this is what students learn in their education to apply these rules. This is all well and fine, so clearly I'm not convinced of arguments from beauty, as you have probably noticed. But we should also look at the past and see how well they have been doing. There have certainly been beautiful ideas that did not work out the way people hoped. The probably best known example are the Platonic solid. This was an idea by Kepler, who thought that if you take the 5 regular polyhedra and stack them into each other, as is shown here, then this would correctly determine the ratio of the orbits of the then known 5 planets. That's a nice idea. It works pretty badly. To begin with, we now know that there are more than 5 planets. Also, the planets do not actually move on circular orbits. But yeah, it was certainly pretty. Yeah, then the circular orbits themselves were somewhat of an issue. They were really popular around Kepler's time. And when Kepler pointed out that actually it would explain the observations much better if those orbits were elliptical, people were strongly opposed to it. They would rather have had circles because circles are perfect. And if God had any choice, then he would have chosen circles. And this is where this whole story comes from with the epicycles, where you make a circle around the circle and then another circle around the circle just to stick with that circle. There was also a peculiar episode in the history of physics around the turn from the 90s to the 20th century in which a group of physicists became pretty obsessed with what has become known as vortex theory. Vortex theory was the idea that the different kinds of atoms that were known at this time were really knots in an invisible ether. At this time, mathematicians had already classified mathematical knots, of which I show you one here. So for a mathematician, knot does not have any ends. And you can classify all the possible knots, and they kind of look pretty in an obvious way. A lot of papers have been written about it. This idea fell very quickly out of favor when quantum mechanics was discovered and described the periodic system in an entirely different way. There was also this idea that was pretty popular at the beginning of the 19th century, that the universe is eternally unchanging. I think this is an idea that people just intuitively thought makes sense. And when it turned out that Einstein's theory of general relativity actually predicts that the universe would be dynamical and change in time, there were a lot of people, including Einstein himself, who were initially very opposed to this idea. And then there were several prominent physicists' late years ideas of unified theories. One example of which is, for example, Werner Heisenberg. He wrote in a letter to his sister, I think, sometime in the 1950s, that these interrelations display in all their mathematical abstraction an incredible degree of simplicity. It's a gift we can only accept humbly. Not even Plato could have believed them to be so beautiful. Heisenberg is famous because he's one of the inventors of quantum mechanics, but he's here not talking about his theory of quantum mechanics, which, by the way, a lot of people thought was really ugly. But he's talking about his approach to a unified theory of all the interactions. And he was at this time pretty convinced that he was on the right track. He actually went around and gave lectures about this. At some point, he must have spoken with some journalist about his theory and have said something to the extent that he has it all figured out, only the details are missing. And this prompted his colleague, Pauli, to write a postcard to his friend Georg Gamow, where he drew an empty rectangle and wrote, "This is to show the world that I can paint like Tizian, only the technical details are missing." So clearly he was not very convinced by Heisenberg's attempt at a unified theory. You've probably never heard of his theory because it worked pretty badly. And after Heisenberg's death, no one pursued it. No, beautiful theories don't always work. And on the other hand, we have ugly ideas that work just fine. Quantum mechanics, for example, a lot of people consider quantum mechanics to be an ugly theory. They seem to be fundamentally opposed to it. I don't count myself among them, but it's certainly something that I hear a lot of my colleagues say. Regardless, quantum mechanics works just fine. It describes our observations incredibly well. Then in quantum field theory, so that's the kind of theory that the standard model works with. We have a procedure that is called regularization. This is a mathematical method which we need because if you try to calculate something that you observe using quantum field theory, pretty often the answer is infinity, which is somewhat embarrassing because that's something you would never measure. Regularization is a procedure to subtract infinity from infinity in just the right amount that you are left with a finite result that actually describes the measurement. And that sounds totally crazy, but a fact is that it does work. And again, it describes our observations very well. Dirac in particular was very opposed to regularization. It was actually one of the reasons that he was pretty convinced that quantum electrodynamics has to be wrong. But it works well and we're still using it. And yeah, then I already said those elliptical orbits, they were initially considered to be pretty ugly. And this idea that the universe changes in time was also considered to be rather unappealing. I should have said this in the beginning, but this is the best example that I could think of for an ugly idea that works just fine, is this flycatcher. Well, how's it looking for beauty? Sometimes it works, sometimes it doesn't. There's also no reason to think that it does work. Our sense of beauty is certainly to some extent hardwired. That is pretty well understood, especially when it comes to us thinking that symmetry is beauty. It's probably because symmetric organisms are more likely to be healthy. There's reason to think that we are actually born with a certain sense of beauty. Beauty also has, without doubt, cultural and social aspects. What you find beautiful depends on what you have grown up with, what you have been exposed to. But neither evolution nor culture prepared us to look for laws that dictate the behavior of things that we cannot see. So there's just no reason to think that this sense of beauty that we have will help us to decide whether a theory for the fundamental structure of matter is correct. Beauty certainly has some experience value. What Weinberg was talking about there with the horse breeder is not entirely crazy. It works as long as you stay within the same circle of theory, within the same mathematical framework. But it is of limited use if you try to develop new theories. But what is it with these aesthetic criteria? They are based on experience, and in many cases, I think it is justified to try to use them initially. But we have no way of knowing that they will continue to be useful. The scientific approach, therefore, would be to use them as hypotheses and see if they work. But in fact, they have not worked for 40 years. And this is why I think we have not seen progress in the foundations of physics, because this has created a vicious cycle. As I said, physics is a fairly mature discipline. The simple things have been done. And now it takes increasingly more time and money to test new theories. we just cannot afford to test all hypotheses that theoreticians come up with. And this means that we must choose carefully which theories to test. If we choose unpromising theories, then this means that the experiments are likely to only deliver negative experimental results, which means that they do not find evidence for new phenomena, but only confirm the already known theories. We do not have any new data that could guide the development of new theories. We get stuck with the unpromising theories, which will be used to commission new experiments, which leads to more null results, which leads to a lack of data, and so on and so forth. I think this is the situation that we have been in for the past couple of decades. Here are some examples for failed predictions in the foundations of physics. The standard model has one number that is known as the theta parameter, which is an unnatural number that people have tried to find an explanation for already in the 1970s. The explanation that they have come up with was to make the theta parameter into a dynamical field, and this field generates a potential, and then the new field rolls down into the minimum of the potential. And that explains why it's small. That's making a long story short. The point is that it was figured out very quickly after this idea was introduced that this means that this new field would be accompanied by a particle. This particle was called the axion by Frank Wilczek, and it was ruled out pretty much as quickly as it had been introduced. What happened after this, however, was not that physicists gave up on this idea that the axion exists. Instead, they came up with a more complicated version of this axion theory and invented something that is called the invisible axion. This is something that people are still looking for with the experiments. For example, the one that is shown in this image. So far, none of the invisible axions have been found. The trouble is that they're invisible. They were deliberately made to be hard to detect. So it's kind of unsurprising that it turns out that they are hard to detect. So another failed predictions is the search for a class of particles that are known as weakly interacting massive particles. That's called WIMPs. The WIMPs are a specific type of dark matter candidates that have been thought for a long time to be very promising. They have been sought for since the mid-1980s. It's really that old. So far, none of them have been seen. You see one of the experiments up there. What has happened here is that every time one of these experiments returns null results, the theoreticians will go and come up with some explanation for why that particle was a little bit harder to detect than they originally anticipated. Since they started making these experiments, the interaction probability has been going down by about a factor 200,000. This image is from an experiment that is called Xenon 1T, which is an upgrade of Xenon 100, which is an upgrade of Xenon 10, which is an upgrade of the original Xenon experiment. And this is not the only kind of experiment that has gone through a similar history. Why did so many theoretical physicists believe that this was true? It was a numerical coincidence that has entered the literature under the name the WIMP miracle. What is the WIMP miracle? The WIMP miracle has meanwhile been ruled out, by the way, but this is how it went. If you have one of those dark matter particles in just the right mass range, so that you can produce it at the Large Hadron Collider, which has not happened. We now know this, but they didn't know this then. And it interacts with the strength of the weak nuclear force, then you can calculate how many of those particles would have been produced in the early universe. And that number comes out to be approximately correctly to describe the observed abundance of dark matter. This is known as the WIMP miracle, and it did not work. Quite a number of failed predictions. I already briefly mentioned this in the very beginning. There were tens of thousands of predictions for new physics at the Large Hadron Collider. Sometimes people are shocked when I say this number, tens of thousands of predictions. That sounds pretty crazy. But what I'm referring to here is, roughly speaking, the numbers of papers that were written about predictions for new particles or extra dimensions or tiny black holes or gravitons and so on at the Large Hadron Collider. There were really that many papers. The papers are still there. If you want, you can go and look them up. But the only new particle that we indeed have seen was the Higgs boson, which was predicted already before the completion of the Standard Model in the 1970s. And I have to emphasize that the prediction of the Higgs boson was not a prediction based on an argument from beauty. The Higgs boson was an entirely different kind of prediction based on an argument from inconsistencies. You could say that this was an old-fashioned good prediction that turned out to work, whereas all those beauty-based predictions did not work. Indeed, if you look at what has historically led to breakthroughs in the foundations of problems, then it was the resolution of inconsistencies in the theories. So, of course, there have been breakthroughs that were entirely led by experiment, where an experiment just discovered something that was entirely unanticipated, and the theories had to be revised in reaction to this. But when it comes to breakthroughs that were led by theoretical predictions, then those were predictions based on the resolution of mathematical consistency. For example, the original notion of space-time symmetry that was conceived by Galileo, the Galilean invariants, did not work together with Einstein's equations of electrodynamics. This is what led Einstein to special relativity. It then turns out that special relativity does not work together with Newtonian gravity, because in special relativity, if you know anything about it, then that it has the speed of light as an absolute limit. Whereas Newtonian gravity, you have an interaction that works instantaneously, so it has no finite time in which it would propagate. This does not fit together. And Einstein set out to resolve this inconsistency, and this led him to the development of general relativity. Special relativity also did not work together with quantum mechanics. This is a problem which was solved by Dirac and led to what we now know as the Dirac equation, which after some more intermediate steps led to the development of quantum field theory, which is still the kind of theory that we use in the Standard Model. And the Higgs too was a prediction based on a consistency problem. If you have the Standard Model without the Higgs, it will just stop working at a certain energy. And this is an energy that we have been able to reach at the Large Hadron Collider that we also would have been able to reach at the superconducting supercollider if it had been built. So from this consistency argument alone, you cannot really predict that it has to be the Higgs. But you can predict from this that something had to happen at the Large Hadron Collider. The lesson that I personally take away from this little history is that if physicists try to solve a problem, they should make sure that it is really a problem, and lack of beauty is not an inconsistency and is therefore not a promising problem to try to solve. Having said this, it still leaves open what I think is the biggest question of all. If arguments from beauty work so badly, why do physicists continue to use them? I mean, it's not like I'm a genius for pointing out that arguments from beauty are not scientific arguments. It is also not hard to see that those arguments, in fact, have not worked since the 1970s. This is all published literature. Really, what is going on there? I think a plausible reason that they keep on doing this is because everyone else does it. It's something that they have learned. They have learned to pay attention to these arguments from beauty. It is probably for many of them a reason why they went into the field to begin with, and they think it's okay to do. So here's an example from Brian Greene's book, The Elegant Universe, where he writes, "Aesthetic judgments do not arbitrate scientific discourse." And then there's some paragraph in between, but it is certainly the case that some decisions made by theoretical physicists are founded upon an aesthetic sense. What he's basically saying is, we totally know that we should not be doing this, but we do it anyway. This is certainly not a problem that is specific to physics. You see the same thing happening in other fields where you have bad methodologies that are not corrected, but are continued to be used even though everyone knows that they're not working. This is something that I learned from a kind of scary book, actually, by Richard Harris, which is called Rigor Mortis, and it's about biomedicine. All the kind of things that are going wrong in biomedicine with mislabeled cell lines and contaminated antibodies, and it's really creepy. But one of the things that I learned from this is that using mice to study diseases in humans is a pretty bad idea, because the results transfer really badly from mice to humans. In fact, a lot of the results that you get from mice do not even transfer to rats. That brings up the question, why then do they keep using mice if they know that these studies are not particularly useful? And the way that Richard Harris puts it is that one reason everybody uses mice is that everybody else uses mice. Another reason is probably that mice are cheap and they reproduce very quickly, but it's not a particularly scientifically good reason. And we have seen a very similar thing happening in sociology and parts of psychology, where people have been using for decades measures for statistical significance that everyone has known to be flawed for a long time. The way that Jessica Utz, the president of the American Statistical Association, put it in 2016 is that statisticians and other scientists have been writing on the topic for decades. So it was certainly something that was well known. Why did psychologists not pay any attention to this knowledge that was in the published literature? This is how a trio of psychologists put it in a paper that they wrote in 2011. Everyone knew it was wrong, but they thought it was wrong the way it's wrong to jaywalk. In other words, they thought it was okay because everyone else was doing it too. They didn't see anything wrong with it. What can we do about it? One thing we can do about it, which indeed is already being done in some of the fields that I was talking about, is that we can look for field-specific ways to prevent the use of bad methodology. For example, this is what people do in psychology and in the life sciences more general right now, is you can impose better criteria for statistical significance. You can also, for example, require people to pre-register that trial. This is something you might want to do to prevent them from changing the hypothesis after they have collected the data, which is a pretty bad idea. Similarly, we could ask theoretical physicists to please not use criteria for beauty. And this would fix the acute problem, but it's bound to come back because it would not solve the underlying problem. Really, what we should be doing is curing the disease. I think the reason that we are seeing these problems of bad methodology becoming accepted practice in so many different disciplines at the same time is simply that academia currently is not working properly. And it's not working properly primarily because scientists do not take into account how being part of a group affects their judgment. They're being influenced by what other people around them think about the research of their friends and so on and so forth. And they take this into account when they're making decisions about what research to do. But it's something that I think they are not consciously aware of. And it introduces a bias in their selection of research projects that they are not currently correcting for. So this brings me to the summary. Using criteria of beauty to assess theories is bad scientific methodology, but bad methodologies can become accepted norm if sufficiently many people reassure each other that they are doing the right thing. Thank you for your attention.
Thank you. Thought-provoking and controversial.
Very sick. I wonder if you heard the talk 10 years ago the prediction might for me to do the gravitational wave. I think that's one of
No, because gravitational waves are a direct consequence of Einstein's theory of general relativity. It's actually, it is really hard to come up with any theory that is consistent with the observations we had 10 years ago, but also much earlier, 50 years ago, and not have gravitational waves. We also have had indirect evidence for gravitational waves already since the 1960s, 1970s. I can't recall precisely, but...
seems like you're indicting what is nation is. Think of beauty, appreciation, art, the change, the impressionists, radical, not appreciated, brand painting, other countries that like to do. Now, like, just sort of the same thing, consistency, which you're making a great case for it. My mind is, which is the opposite. But it seems like there still might be a place for beauty, kind of find it for rethink.
Yes, you're right. So what I'm really criticizing is a very narrow sense of beauty that has become accepted norm, not so much the reliance of beauty in general. You could, I would make a point that if you have a theory that describes nature, that is beautiful in and by itself.
If I take what say logic concept that the what you should do, or scientists look at the foundation of physics, they do what they should ask where it is cosmic theory, where it is one, and that is the inconsistency between the relativity and quantum mechanics. And then would say this, that the next step is we would ask where does that to become manifest, and it is at the bound scale. But it's hard to do experiments at that the probability is still 16 orders of magnitude away. What you have any suggestions there are many to be addressed and based on if you actually get.
Yes, for starters, I have to disagree with what you just said because you are using the word Planck scale in a rather sloppy way. What you're saying is correct if you think that you need to reach energies at the Planck scale, or say to reach a curvature that is at the Planck scale to actually see the quantum effects of gravity. But that is not correct. We have actually known this for a long time, that this is not the only way to see quantum effects of gravity. And the reason is fairly simple, though often neglected. It's that gravity becomes stronger the more mass you pile up. With piling up mass, you can also amplify the quantum effects of gravity. So really the problem that you're facing is that either you have a system that has pronounced quantum effects, say in a particle collision or something like this, but then the particles are so light that you cannot measure the gravitational field. Or you have a system that is heavy enough so that you can measure the gravitational field, but then it does not have quantum properties. Now, it's interesting that while we have not made a lot of progress on the first point, we're probably not going to reach the Planck scale with particle colliders anytime soon. A lot of experimental progress has been made in bringing heavier and heavier objects into quantum superpositions, which opens the possibility that you could just go and measure what happens to the gravitational field in these situations. And there are some groups on the planet which are trying to push this limit. They're not quite there yet. They're maybe 3-4 orders of magnitude away. So there's still this mismatch that either you have a heavy object that does not have quantum properties, so then you can measure the gravitational field, or you have managed to bring it in a quantum superposition, but then you can't measure the gravitational field. There's still a gap to bridge, but we're not talking 16 orders of magnitude. We're talking 3 or 4 orders of magnitude, and that in a field where the technological development at the moment is pretty rapid. So this is one thing that I think should definitely been done, and that deserves much more attention. For example, it's pretty ironic that while there are, meanwhile, experimental groups trying to push this limit, there are basically no predictions from the theories because the theoreticians never looked at their case. It's I find this very amusing. There's also, I was emphasizing here theoretical predictions when it comes to inconsistencies. But of course, there are also inconsistencies between theory and data. And so dark matter is a case of that, where we already have some inconsistency that certainly deserves more attention. And if, for example, if we were to understand better what is going on with dark matter, is it a particle or is it a modification of gravity, then that might tell us about something else. And we might be able to actually develop a better theory, which would then help us to make predictions that we could go and test, say, with a specific experiment. But you have to know where to look. Just guessing clearly is not working if you look at the past 40 years. And then there's also, I like to mention that personally, I think that the measurement problem in quantum mechanics is an actual inconsistency. It's an inconsistency between quantum mechanics and reductionism. So on the one hand, we think that reductionism must be right, and we have a lot of data that supports it. On the other hand, in quantum mechanics, we need to make this additional assumption that tells us what happens in a measurement process, which is a macroscopic phenomenon. So if this theory was consistent, then we should be able to derive from the theory what happens in this measurement process, but we can't. I think this is an inconsistency, and it's one that presently basically attracts no attention. Though I want to emphasize that this is my reading of the history. This is the conclusion that I've personally come to, that we would be well advised to focus on resolving actional inconsistencies. If someone else comes to a different conclusion, that is also fine by me. What I find very troublesome is that the people in those fields don't remotely seem to be bothered by that lack of progress and don't want to contemplate what has been going wrong here.
Yeah. You talk a lot about the thing theory, but obviously that they are but huge amount of groupthink experiment. I would say we're still using the same experiment. We're great. Well, yeah, there's not here to tell it that basic stuff. I don't know what it. Part of it. It is the groupthink. There's groupthink in theory. There's in terms of more familiar knowledge, tinkering.
I'm not an experimentalist. I have had very little interaction with experimentalists here and there, but it's not something that I really can comment on. I can only say the obvious, which is that social reinforcement, that's a polite word for groupthink, is something that we're all subject to. It's just a risk for every one of us. And by default, you should expect it to happen in any collaboration, in any community, unless people take steps that can prevent that from happening. The first step to which is an awareness that this is a risk.